Have you ever wondered whether empty space is truly empty? At first glance, a vacuum seems like pure nothingness, a region without matter, light, or activity. Yet modern physics suggests something far more intriguing. Even the emptiest regions of space may contain fleeting activity at the quantum level, where particles appear and disappear in ways that challenge everyday intuition. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today we explore virtual particles and the physics of empty space. This topic sits at the intersection of quantum mechanics, field theory, and cosmology. It reveals that what we call nothing may actually be a dynamic environment shaped by fundamental physical laws. To understand virtual particles, we first need to consider how physics describes reality at very small scales. Classical physics once pictured particles as tiny, solid objects moving through empty space. Quantum theory, developed during the early 20th century by scientists such as Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, replaced that view with a more complex picture. In quantum field theory, which matured during the 1940s and 1950s, particles are excitations of underlying fields that exist everywhere in space. For example, an electron is not simply a point object. It is a localized excitation in an electron field that permeates the universe. Photons emerge from the electromagnetic field. This framework means even a perfect vacuum still contains fields capable of fluctuating. The uncertainty principle, introduced by Heisenberg in 1927, plays a central role. It states that certain physical quantities, such as energy and time, cannot both be known with unlimited precision simultaneously. One implication is that very short-lived fluctuations in energy can occur without violating conservation laws, provided they vanish quickly enough. These transient fluctuations are often described as virtual particles. Virtual particles are not particles in the ordinary sense. They cannot usually be directly detected as free objects. Instead, they appear in calculations describing interactions between measurable particles. Physicists use mathematical tools called Feynman diagrams, developed by Richard Feynman in the late 1940s, to represent how particles exchange virtual particles during forces such as electromagnetism. Although virtual particles are theoretical constructs, their effects have measurable consequences. One well-known example is the Casimir effect. Predicted in 1948 by Dutch physicist Hendrik Casimir, it describes how two closely spaced metal plates in a vacuum experience a tiny attractive force. Experiments beginning in the late 20th century confirmed this effect with increasing precision. The force arises because quantum vacuum fluctuations behave differently between the plates than outside them. Another phenomenon linked to vacuum fluctuations is the Lamb shift. In 1947, American physicists Willis Lamb and Robert Rutherford measured slight energy shifts in hydrogen atoms that could not be explained by earlier theory. Quantum electrodynamics, incorporating virtual particle interactions, successfully accounted for these differences. This marked one of the first precise confirmations of quantum field theory. Empty space also plays a role in cosmology. The concept of vacuum energy suggests that even space devoid of matter possesses intrinsic energy density. Some cosmologists connect this idea to dark energy, the phenomenon responsible for the accelerated expansion of the universe discovered in 1998 through supernova observations. While the relationship between vacuum energy and dark energy remains under investigation, both highlight the physical significance of empty space. Black hole physics offers another intriguing connection. In 1974, British physicist Stephen Hawking applied quantum theory to black holes and predicted what is now called Hawking radiation. According to his calculations, quantum fluctuations near a black hole's event horizon can result in particle pairs, where one escapes as radiation while the other falls inward. This implies black holes may slowly lose mass over extremely long timescales. These discoveries challenge the everyday notion that nothing is simple absence. Instead, the vacuum becomes an active participant in physical processes. Forces, radiation, and particle interactions can all reflect underlying field behavior, even where no ordinary matter exists. It is important, however, to separate scientific understanding from popular misconceptions. Virtual particles are sometimes portrayed as literal particles constantly popping in and out of existence everywhere. While this imagery helps visualization, physicists emphasize that virtual particles primarily represent mathematical aspects of quantum field interactions. They are tools for describing how fields behave, not necessarily miniature objects flying around in empty space. This distinction matters because quantum field theory is highly precise mathematically. Predictions derived from it, such as the anomalous magnetic moment of the electron, match experimental measurements to extraordinary accuracy. Maintaining clarity about what theoretical terms represent helps preserve that precision. Research into quantum vacuum properties continues today. Experiments in high-energy particle physics, condensed matter systems, and astrophysical observation all probe how vacuum fluctuations influence measurable phenomena. Facilities like CERN's Large Hadron Collider, operational since 2008 near Geneva, explore particle interactions at energies that may reveal new quantum field behavior. Quantum optics laboratories also investigate vacuum effects using ultra-sensitive detectors and laser-cooled environments. These studies help refine understanding of fundamental forces while contributing to practical technologies such as quantum computing, precision sensing, and advanced communication systems. The implications extend beyond laboratory physics. Early universe cosmology suggests quantum fluctuations shortly after the Big Bang seeded the density variations that eventually formed galaxies. Observations of the cosmic microwave background radiation, especially by satellites like COBE in 1989, WMAP in 2001, and Planck in 2009, show subtle temperature patterns consistent with this idea. Thus, quantum fluctuations may have shaped the large-scale structure of the universe itself. The galaxies we observe today could trace their origins to microscopic variations in an early quantum vacuum environment. Philosophically, this perspective transforms how we think about nothingness. Classical philosophy often treated empty space as absence. Modern physics suggests emptiness possesses structure, energy, and measurable influence. The boundary between something and nothing becomes less clear than intuition suggests. This shift parallels earlier scientific revolutions. Before atomic theory, matter seemed continuous. Before relativity, time seemed absolute. Before quantum physics, determinism seemed universal. Each new framework expanded understanding while revealing deeper complexity. Yet uncertainty remains. Physicists continue searching for a unified theory, combining quantum mechanics with general relativity. Current quantum field theory works exceptionally well for particle interactions, while Einstein's general relativity describes gravity and cosmic structure. Reconciling the two consistently remains an open challenge. Some proposed approaches include string theory, loop quantum gravity, and other speculative frameworks developed since the late 20th century. These ideas attempt to explain how space-time itself might emerge from more fundamental quantum principles. Evidence remains incomplete, and research continues actively worldwide. Despite unanswered questions, the concept of virtual particles illustrates a broader lesson. Scientific knowledge evolves through observation, theory, testing, and revision. Early quantum theory seemed counterintuitive. Over time, experiments confirmed its predictions repeatedly. Today, it underpins technologies from semiconductors to lasers. Understanding empty space also influences technological development directly. Vacuum engineering enables particle accelerators, electron microscopes, and spacecraft instrumentation. Quantum field insights guide materials, science, nanotechnology, and advanced electronics. For learners, virtual particles provide a gateway into deeper physics. They connect mathematical theory, experimental evidence, and philosophical reflection. Exploring them encourages critical thinking about how science defines reality. At a cosmic scale, the idea that empty space has energy influences predictions about the universe's future. If dark energy relates to vacuum energy, cosmic expansion may continue accelerating indefinitely. Alternatively, new physics might alter that trajectory. Ongoing observation aims to clarify these possibilities. Ultimately, Studying empty space reminds us that absence can still hold complexity. The vacuum is not merely a stage where physics happens, it is part of the play itself, shaping interactions, forces, and cosmic evolution. Next time you think of space as empty, consider the invisible fields, fleeting fluctuations, and quantum processes that may be present. The universe often hides its most profound activity where we expect nothing at all. This is Mattermosaic, piecing together the universe, one discovery at a time. If exploring the hidden physics of empty space sparked your curiosity, share this with someone fascinated by the deeper layers of reality, and tell us what scientific mystery you would like to explore next.